split. So we have 0, 5, 8. At this time, we don't need all these pointers. Right? Copy. Just exactly same as what you did in the list. And which one is the middle value? 5. And left hand side goes to left hand side, right hand side goes to right hand side. Then what about the middle value? Middle value? Commutative. Do we have space? No, we can create because we do not have to have. Five goes to here. Yeah. Data point, data point, data point, data point, data point, data, not this one, and data point. Okay? That's it? Not yet. We need to finalize this less than, oh, this is not 0. One should be 1, right? Middle value is 1. Less than 1 goes to here. Bigger than 1 goes to here. And less than 8 goes to here. Bigger than 8 goes to here. Any question? Who got the same answer as this one? I want to be extra. Yes?
Link. What's the use for link? Always to the left or?
Which one? This link? The pointer?
Yeah.
Pointer, when you need a pointer, so check the whether patterns will divide the data, right? Based on the key entry. Left hand side means less than this value. Right hand side means bigger than this value. So which means less than 5. All value less than 5 goes to left hand side. This. And bigger than 5 goes to here. So that means what if we insert the data 4 in this case? 4, even though we have space over here, we do not use this one. First, find the leaf node. Okay? So 4 is less than 4. So this parent, this children node. Even though we have space, first we need to find the leaf node. Why? Because it's the bottom of approach. So bigger than 1. So there's a space, fortunately, so we can create the 4. Okay?
4 is bigger than 1, 0, and 3.
Yeah, it's a bigger than 1. That's the reason it's the right hand side of 1. So go to here.
So right hand side is also the.
Right hand side means this one, inequality.
Yeah, but why not beside the 1? 4.
So 4 is bigger than 1. What's the problem?
No, and why it's beside the 3? Why it's not beside the 1?
The 3 is already inserted by following the same algorithm. So it's bigger than 1. Okay? All value in this children node is bigger than 1.
So you mean when I start filling up
Yes.
line 4,
Yes.
then I start from the bottom.
Yes, you need to find the bottom node first, where it goes. Okay? Okay. Any question? This is your project E. Okay? Second project. First, you need to understand the algorithm, then implement it. Okay? So, why don't you see the handout, project B handout. Okay? In the project B, this is the optional project for undergraduate students. How many undergraduates? So we have 1, 2, 3. So it will be optional. So if we want to get the extra point, so you can solve the problem, then submit it. Otherwise, it's okay. Okay. So, but it's a mandatory for graduate student. It's an individual project. In this project, you are going to build a B3 indexing structure. If you already build something data structure in your algorithm course, it's quite similar to how you implement the linked list, right? In your algorithm course, what the data structure course. It's the same thing. So indexing is not the special thing or special program. It's the same as what you did in your algorithm course. So you are going to build a B3 indexing structure. First, you need to understand the algorithm. Who will implement lookup? What is a lookup? You need to find where inserted data, input data will be stored. Okay? By checking the key value, index key value. And next, insert. Then, once you identify the node, you need to insert. Insert means add the key value. Okay? If needed, you need to sort inside the node. And display. Display means display the indexing structure. Update is not mandatory, but if you want, you can easily implement this one. Tools. Finish success to implement successfully in this B3 indexing structure. First thing is you need to understand the algorithm, then define the node structure correctly. Okay, this is the first step. So how can we implement the node structure? It can be object. It can be construct in C program. It can be any type of data structure as long as they can keep the number of entry with the pointer. What is a pointer? Pointer can be not the address, memory address or hard disk drive address. No. In this case, you can use assign block node ID. Whenever it's created, you can assign the node ID 1, 2, 3, 4, 5, 6, 7. Then this one value is a 4. Just. That's it, right? So pointer is not that complicated structure. It's nothing but node ID. So for your help, I already uploaded skeleton of B3 indexing structure based on Java. But if you are not familiar with the Java, you can use any program language. C, C++, .NET, C#, ASP, whatever you want. Okay? But algorithm should be identical. Okay? So, first, why don't you take a look at skeleton program? So even though you do not know the Java, you can understand that skeleton program. Okay? So how to define the node structure and how to keep indexing, entire indexing. Some of the students prepare list or vector or the what else? Object. So you have an index object inside the object. You can keep the node object. Then there's a method, like a lookup method or others. The insert method, display method. But there are a bunch of different ways. So this is the second project. And also, if you can implement, if you successfully implement, then why don't you think about the display? You don't know whether my indexing structure is correct or not, right? So the display. So if you are using command line interface, okay, at that time you can be smart to display your output. Like the first line is for first node. Then second line is the first generation of the node. And third line, this one, and provide the node ID because you cannot draw the arrow and something like that. So you can be creative.
So we can print it out in console.
Yeah, you can use the console. It doesn't matter. As long as I understand your indexing structure. You should have the at least insert. Okay? So when I test your program, I will insert the data using, so input can be 5, okay? Or the input can be interactive. So I type the number, then display your indexing structure. Any question? first way to try, then probably maybe next week I will explain one more time. Once you start, probably you will stop or you will be struggling. So at the time I will explain a little bit more tips about this one. Then this is a B-tree structure. Can we use this indexing structure for real index? It's not done yet. We have one more D plus 3 structure. What time is it? We have 12 more minutes. That's enough. It ended 2:45, right? Okay. So this is a B3 index. B3 index structure. Is it balanced? Yes, so balanced. So we can use this structure for real DBMS. But we realize once after we apply this indexing structure to real database, we got the problem. Can you guess what is the problem? In terms of a query processor? Query processor would like to use this indexing structure to find fastest way. Okay? This is kind of the fabric, right? So this index suggests why don't you use this index to go to Manhattan? But we realize after we apply to this one, we realize there is a problem. What is the problem? Yes? Kim, is it really balanced? Take a long time. Why? Take a long time is not that important. The more important thing is fairness, guaranteed. Whether this one is guaranteed or not. My route go to for the Manhattan takes 1.5 hours guaranteed, plus minus 1 minute margin. That's the best one. Even though average the travel time of the I-95 is 30 minutes, it's nothing but average. Sometimes it takes longer time. So we have such a problem. In other words, is it really balanced? Blank. So, what about 3? I'd like to access 3 here. How many IO do you need? 1, 2, 3, 4. Yes. What about 0? 1, 2, 3, 4. What about 1? 3. 1, 2, 3. What about 5? 1, 2. They are different. Okay? It's not fair. There is the upper limit, right? Maximum 1, 2, 3, 4. But sometimes 2, sometimes 4. So it's better than 33, but not entirely balanced yet. Because of what? Because of this internal node. So in case it's small, index is fine. What if we have the 10 millions of data? Sometimes it's fast, sometimes the number of gaps is bigger than 20, sometimes 30. Okay? So it's not guaranteed. We try to enhance, extend, improve this B2 index. How? Which means 100% balance. We do not keep index key entry internal node. Instead, put down all the values, all the index key entry to the leaf node. Okay? Then internal node will be used for what? Only divide the data. So 5 means 5, in this case 5 means index key entry plus this pointer. But in this B plus 3, we do not have a data pointer. Instead, only 5. 5 will be used for separate. Okay? Then 5 will be somewhere here. leaf node. This is called B plus 3 is the variance enhanced version of B3 index. That is a B plus 3 index. 99% of index in relational database management system use B plus 3 index. We will see that example. Okay. So, first we need to define node structure. There are two different types of node in B plus 3. Because internal node does not keep data pointer. Only leaf node keep data node pointer. Okay, so in case of B plus 3, in case P is equal to 3, okay, that means internal node and like this. Actually, we don't need this. Just key value K1. It's just nothing but value. There's no pointer. Okay? No data pointer. This is called internal node. And leaf node. Leaf node P, there is a P leaf, that is a P minus 1. In this case 2. Leaf node does not need children pointer because it's a terminal node, last one, okay? Without any children. So we don't need actually this one for leaf node. Instead, we need data pointer, key entry, K1, K2. How many index key entry? 2. And this. I do not explain this one yet. I will explain later. Okay, so this is actually from data node structure from B3 index is split into this part. Okay, so this is the node structure, leaf node and internal node in B plus 3. The algorithm is almost the same as B3, but a little bit slightly different. So we will understand using the same data. So first we are going to insert A. Okay? Same thing. We do not have this one. First, which one do you need? Internal node or leaf node? Internal node? Internal node does not have data pointer. So we need leaf node first. Okay? So leaf node. A is inserted, and next 5, like that. Okay? Then this is the data pointer, point to this one, point this one. Okay? So this is the B plus 3 index. It's the same as B3, but using only leaf node. Next, what happened? 1 is inserted. No more space. What does that mean? Full. In case of full, you need to split. Split means copy. So we have 1, 5, 8. Okay? Find middle value. Which one is the middle value? 5. Okay? 5 will be raw material. So we need, at this time, this is called the leaf node. We need internal node, this. So 5 will be inserted like that. Is it the same as the B3 index? Actually not. Why? B3 index need data point. But this one is not. Because we don't want to keep the index key entry internal node, only leaf node, which means left hand side, which value?
1.
1 and up to middle value goes to left hand side. And which means 5. The other right hand side go to right hand side. What's the difference? What is the different thing from B2 index? First, there is no data pointer. Instead, middle value goes to here. So, in B+3 index, including middle value, up to middle value, lowest to middle value goes to left hand side, and the other goes to right hand side. That's the main difference. So, that's it. Not yet. You need to finalize this. Okay? So this is the B+3 index. First, this one is different from the B3 index. There's no data pointer. So when you access the data file, how can you access it? 1 equal or less in this case. B+3 equal or less goes to left hand side, this node. And finally, you will get 5 data pointer that access the data. Well, how many? 1, 2, 3, access. What about 1? 1, 2, 3. What about 8? 1, 2, 3. Always 3. It's the balance. Okay? Perfectly balanced. It's done? Not yet. There's one more important thing in B+3. We do not use this one here. This is called sibling pointer. Sibling. Okay? My brother and sister. What is the sibling node of this one? This one. So, sibling pointer point to the next node. Okay? Why do we need sibling pointer? Anyone? I will give the extra point. Yes. Connect what? Yes. Why do we need this sibling pointer? When do we need? No? Hint. In B+B3 index, when we access sequential search, 1, 2, 3, 4, 5, 6, how can you access the data? 1 is here. So 1, 2, 3, and 2 is here. 1, 2, and 3 is here. 1, 2, and 4 is here. 1, 2, and 1, 2. In sequential search, you need to up and down, up and down, up and down. It takes a long time. What about B+3 index? Anyone? You still have a chance to get the extra point. Answer?
It's not up down.
Oh yes.
You don't need to go up and down. You can just go straight.
Linear. Okay, using what?
Using the sibling pointer.
Sibling pointer. So 5. So first you need to find 1. 1, 5, then next, using sibling pointer. So because of that, B+3 is more efficient to support linear search, like inequality condition in sequence. So that is the sibling pointer. Next, move to the next. Which one is the next value? 7. First, you need to find the leaf node. 7 is bigger than 5, and fortunately we have space. So 7, 8. I do not have enough time today to check your midterm. Definitely I will check the next class. Okay? I wrote, but I need to complete this one today. Okay, then next 3. Where it goes? We have space, so we can we insert the 3 over here? No. Always leave no. So 3 is here. It's a full. What happened? We need to split. Okay? 1, 3, 5. So we have 1, 3, 5. Find the middle value. The middle value will be promoted. Insert the 3. So we have space. 3, 5. And 1 goes to here. 1 goes to here, and 5 goes to here. What about 3? 3 is left hand side. Then check the children pointer. Less equal or less than 3. Equal or less than 3 goes to here. Bigger than 3, equal or less than 5 goes to here. Bigger than 5 goes to here. That's it? No, not yet. You need a sibling pointer. Don't forget sibling pointer. Because of that, you lose a lot of points in the final. Okay, the next one is 12. 12, can we use this one? For 12, we don't know. We need to check where it goes. 12. 12 is bigger than 5. Then we do not have space. We need split. So 7, 8, 12. So 7, 8, 12. This is the middle value. We insert the 8 over here. So this is a 12. Then check. Oh, we do not have space over here. Then follow the same thing. So copy 3, 5, 8. Which one is the middle value? 5. So comma. So 5. This is an internal load without data point. And what about here? 3 or 3, 5. We need only 3. Why? Internal load will be used for divide. Okay? It's just less than 5. Okay? Bigger than 5. So we need only 3. And here we need 8. So less than 5 goes to here. Equal or less than 3 goes to here. Bigger than 3 goes to here. And bigger than 5 goes to here. Equal or less than 8. And bigger than 5 goes to here. 8 goes to here. Don't be confused. Here, this is the same as the B3 index. Yes?
What about 5? Means 5 there.
5 is not here. Why? The internal load is used for what? Distribute. Okay? It will not have data pointer. Data pointer is over here. When you search data 5, you need to go here, 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 and finally data point. And we did 12. 9. 9 is where 9 goes. Bigger than 5, bigger than 8. Finally, we have space. 9, 12. What about 6? So we have space. Can we insert the 6 here? We don't know. We need to check. 5, 6 is bigger than 5. So goes to here. And 6 is less than 8. So it should be inserted in this node, even though we have space over here. Okay? If you put the 6 here, you cannot retrieve the 6 because this sign is less than 5. Okay? So how can we can split 6, 7, 8. 6, 7 goes to here. And 8 goes to here. 7 will be promoted. We have space, fortunately. So equal or less than 7 goes to here. Bigger than 7, equal or less than 8 goes to here. Bigger than 8 goes to here. Then sibling point. Okay? What about 0? 0 is less than 5, right? And less than 3, supposed to be here, no space. We can insert 0 and 1. And this is the 3, and 1 will be promoted. There's a space, 1, 3. So 4 or less than 1, 2, 2. Okay? This is a B plus 3 index. Then, let's search. What about 0? How many IO do we need to access 0? 1, 2, 3, data pointer 4. What about 5? 1, 2, 3, 4. What about 12? 1, number of IOs are needed, then the query processor are convinced to whether this index is faster than the others. Okay, always it takes a 4 IO. Right? If another index takes a 6 IO, which one is better? This one is better, faster. So recommend this one. That's the idea of query processing. Okay, so that is the B plus pre index. Okay, so in your project you will implement the B3 index, not B plus 3 index. Okay, so why don't you go when you go back to your home, why don't you understand the B3 index first? So for your practice,